Newton's laws is, and it is in this form possibly we are seeing Newton's law in our day in day out exercise. Everything behind possibly goes in background, but I just wanted to brief you about all this background story. Yeah, so the point is this, that the translatory motion of the body means you can lump the mass at the center of mass and treat it as a particle. And the third law in the strong form, as I said, is equivalent to the conservation of angular momentum of a pair of particles. For continuum mechanics like mechanists like Parag and others, there are two important laws. I mean, there are quite a few of them: mass balance, momentum balance, angular momentum balance, laws of thermodynamics. But angular momentum balance does not feature in Newtonian scheme of things because it's the third law, and angular momentum balance can actually be derived. Okay, so therefore it's not a law. So the strong form of the third law is effectively the conservation of angular momentum in a very disguised fashion. With that, you can see the derivation given in very classical textbooks. You can also derive the result that rate of change of angular momentum is equals to applied torque. So that also can be derived, and that together with the Newton's law will finally give you what is known as the Newton-Euler equations of motion. And on record, I hang my head in shame to note that most of us live and die as engineers without knowing the Newton-Euler equations. Okay, we know the Newton equations of motion, which is true for planar systems, but we never graduate to the three-dimensional motions, which is the Newton-Euler equations of motion. The complaint is, oh, it involves the inertia tensor, and people get tensed about tensors, and there are some humanitarian issues, and we let it go at that. Okay, entered D'Alembert. This is my favorite. Everything about D'Alembert, I think, is misunderstood. Starting from his name, we pronounce it as D'Alembert, which is not correct. Okay, but at the age of 40, I cannot change my habit. I will keep calling him D'Alembert. I learned from YouTube video that he is called D'Alembert, something like that, but I cannot make it up right now. I will keep calling him D'Alembert. I hope his soul rests in peace and do not scare me in my dreams about that. But more importantly, I think we have grossly misunderstood his point. Everywhere you see, and this includes this very authoritative book by Euler, and this is given in very stark highlights in a box, that D'Alembert's principle is F minus ma equals to 0. Newton's law is F equals to ma. D'Alembert's law is F minus ma equals to 0. What a great idea. So therefore, the other research ideas that should follow is ma minus f is also equals to 0, and that should be a paper. Okay. Fi means the component of f in some ith direction, divided by mass times acceleration in that direction should be 1. That should be another paper. Okay. And at this rate, I am sure we can get papers after papers, only if the DC member is, or the reviewer is not someone who knows this trick. Okay. So these ideas don't work, right? So somewhere we have missed this point, and this has been beautifully brought forward by this cartoon, which my student Ajinkya has done. If D'Alembert were a cook, he actually said many things. He actually cooked a lot of foods. This is my favorite non-veg item. This is possibly curd rice, which is not so much my favorite, and these are some soups. But it seems that in the party, everyone, whether it is this nutty professor with a spectacle and bald head, I don't have a bald head as yet, so I am not this man, the girl or the boy or whatever, everyone is lining up towards this bowl of curd rice, which is just f minus ma equals to 0. But believe me, this is not what he said. He had other issues also, which is just completely overlooked, right? And that's why his soul does not rest in peace and does not allow me to rest in peace. Okay, it keeps telling me that we should correct this for sure. Okay, so before correcting this, let me point out some other issues which are there in the usual textbooks. Oh, okay. Yeah, so Craig and Miriam again, virtual principles. Yeah, another point is about virtual displacements. What are virtual displacements is a very uncanny thing. So, Craig and Miriam says it is any assumed any arbitrary displacement, and some of my students also say so. Anything is virtual displacement. Oh, I can assume anything and get away, that seems too good to be true. Beer and Johnston does better. Since the displacement considered actually does not occur, it is virtual. Okay, it does not occur, but then why should I study it? It is not occurring, let it go. Okay. Hibbeler, imaginary assumed virtual movement does not actually exist. Okay. Again the same question, if it does not exist, and all my students keep saying Hilbert space does not exist, why are you so very cranked up about Hilbert spaces? We live in R3, we die in R3, okay, 3-dimensional real space. So why are we so bothered about these things? My same questions comes back to them, that why are we bothering about these virtual displacements, principle of virtual work and so on and so forth, if they actually don't exist, right? Further questions. This happens in thermodynamics also, Professor Babu is here. Dx, delta x, triangle x, these are all over the place, and we just give it up after a point, that what is the difference between dx and delta x in particular. Both seem roughly the same, right? I mean, is something that is cause of concern. Then virtual displacements are supposed to be small. Yeah, I didn't say that, but all of these authors say they are small. Again the question comes, how small? 1 millimeter, 1 nanometer, height of Abhijit Sarkar, which is small. What else do you want? Okay, what is smallness? Smallness can never be quantified. Okay. And the most important question in 2018, what is virtual about this virtual displacement? Because today we are living in the age of virtual reality, and we tend to believe that everything which can be simulated is virtual. So do you mean to say in D'Alembert's time, this was like a simulated displacement and that's why it was called virtual? I don't know at this stage. This is a very interesting question that I have heard in IIT Madras often. Can this be found experimentally? Okay. Unfortunately, virtual displacements cannot be found experimentally. Then it does not exist, because my reviews have been like that. You cannot test it experimentally, then it's not worth. Okay, fine. Let's go ahead. This is also an interesting question. You are taking real forces, marrying them with virtual displacement, and then the children are called virtual work. Real displacement, real forces, virtual displacement produce virtual work. There is the complementary principle also. Virtual forces, real displacement produce complementary virtual work. It's all very confusing, right, at this stage. Okay, so this has to be understood. I am sorry, this is the only example I know by which I can convince you about what a virtual displacement is. Virtual displacement is something wherein the time is frozen. This is against the principle of real dynamics, real mechanics. Real displacements, whether small, large, medium size, potbelly size, nothing can happen without the lapse of time. But when you talk about virtual displacement, you have to hold on to this idea that time is frozen. And I know you cannot think about this. The only place where I could think about this is in this land of Kurukshetra, where everyone is confusing you. There is this one Lord who holds time constant and delivers his sermon to Arjun. Time is frozen. Okay, that's virtual displacement. That's the most important characteristics of virtual displacement. Because time is frozen, all the forces that are there, whether constraint forces, whether action, reaction, whatever you call them, are held fixed. They do not change. This also cannot happen for real displacements, which is why you cannot measure them. They must be kinematically admissible. That means Arjun keeps on the ground. He doesn't go dig a hole and go inside. Similarly, he doesn't fly off from the ground. His constraint is he has to stay on the ground. Okay. So all the constraints has to be enforced. The kinematic constraints, which asks the body to remain where it should be. If it is on this surface, then I have to remain on this surface. But the virtual displacement of that I am taking now cannot violate this constraint that I have to stay grounded. Okay, so that's what I mean by kinematically admissible, and it also has to be infinitesimal. So that captures the notion of smallness. When I say small, I actually mean infinitesimal. That means second order terms in your Taylor series are not important, right? Everything can be linearized around that first term. Yeah, so dr, coming back to the other question that I have asked, dr is the infinitesimal displacement that takes place during the infinitesimal time dt, whereas delta r is the virtual displacement which actually takes place without the lapse of time. And it is for this precise reason that whether in 2018 or 3018, you cannot measure virtual displacement. I can give it to you in writing. No one can measure virtual displacement, but virtual displacements are there in our formulation, and it is very important also. Your entire workhorse of solid mechanics, FEM, runs on this. Okay, so when you say virtual displacements are just useless, be careful. Okay, so just elementary calculus, if r is a variable which depends on these parameters, when you say dr, the theorem of what is it called, total derivative, tells you that this term is there. When you take the virtual quantity delta r, you do not account for this term because the time does not change. Okay. So with that, let us come to the principle of virtual work. So the way I like to understand this as follows: if you have any equation Ax equals to b, and you want to solve this equation, then instead of solving this equation, you can multiply with y transpose, where y transpose y is an arbitrary vector. So y transpose Ax must be equals to y transpose b. So these and these are effectively the same mathematical statement. For any x which satisfies Ax equals to b, alternately you can say that for all y, y transpose Ax must be equals to y transpose b. We do exactly the same sort of things here. Okay, first let us go one step backwards and talk about the statics. In the Newtonian approach, we will have the external forces, which is capital F, and the constraint forces small f. So for each particle, for each body, you add up the external forces and the constraint forces, and since it is not moving, you are saying that it is equals to 0. So it must be in equilibrium. Now when you are saying the principle of virtual work, you are forgetting about these constraint forces. So the constraint forces are no longer important. So my statement of principle of virtual work, and you can quote that in the footer of your emails. This is also a very philosophical statement, that constraint forces are virtually workless. This has ramifications in real life also. Any force which is trying to constrain you, you must understand that they are virtually workless. They have no other work. Okay. So keeping that philosophy aside, I think it is really remarkable that we have a law of mechanics which just says that forget about these constraint forces, just work with the externally applied forces and please sum it over. This summing operation is this y transpose operation. If you know what is your inner product, you will be able to show that this is effectively the same as this. So the real power of principle of virtual work is in the elimination of this quantity, which is the constraint force. Okay. So the constraint force is no longer important. That's principle of virtual work, and it is precisely this that D'Alembert's principle has now incorporated into the dynamic systems also. So the dynamical systems, the D'Alembert's contribution is this, that in the Newtonian approach you say mass times acceleration is equals to the sum total of the forces, where the sum total does include the applied forces as well as the constraint forces. But now you get rid of the constraint forces and you just say F minus mi Ri times these virtual displacements and sum over all the particles is equals to 0. So again you get rid of these constraint forces. So that's why Ajinkya shows it very nicely that the constraint forces are a very important recipe of this D'Alembert's principle, which is never talked about, right. Similarly, virtual displacement is a very important recipe of this D'Alembert's principle, which is never talked about. Okay. We only pick up a part of, just pick up this part of the story and sell it as D'Alembert's law, and believe me, that's why his soul is not resting in peace. Okay, we should correct ourselves. Okay, so in case forces are not needed, this principle of virtual work is very effective, and it's a fundamental axiom, and those of you who are still doubting me, believe me, you will not get placed, because all your placement interviews will be in FEM, industry likes it, that is what is called Galerkin method, and that is principle of virtual work for you. Okay. So, you will have the curse of your employers if you do not believe me right now. Okay, I have one more story to tell you, which is about vectors and tensors. Vectors are useful because they have been taught in my primary school, and I do not argue with my primary school teachers. Okay. Whatever has been taught in primary school and possibly undergraduate, yeah. No, secondary school. Okay, because it was taught with a cane on my hand, on the hands of the teachers. So, it just went in, and this is that cane which vectors, I understand, I can draw it. It's an arrow, it's representable by arrow, nothing great about it. It has magnitude, direction, some say it has sense, but I think that is nonsense, so we'll leave it at that. With the choice of coordinate system, essentially, it boils down to be to these three numbers that you want to express what is its length in the x direction, y direction, z direction. So, it's essentially these three numbers. So, therefore, the question is anything that is expressible in three numbers a vector? I am expressible by my Aadhaar number, at least I am supposed to. So, it's a 12-digit number. So, have I become a 12-dimensional vector? I don't think so. But here are more important qualifications of a vector. Vector must abide by rules of vector algebra and coordinate transformation, and it is precisely here that rotations fail to be a vector. Rotations are also expressed by three numbers. Okay, you call them Euler angles, you call them axis angles, whatever you want to call them, you call them. But just the mere criteria that it is expressible by three numbers does not mean that it is a vector. It is a triplet, but it is not a vector. Interestingly, the derivatives of rotation, in some sense we understand angular velocity as derivatives of rotation, angular velocity becomes a vector. This is very strange, but that is a fact of life. We cannot prove it in this 1 hour session, but angular velocity does become a vector, which essentially means that the integral of angular velocity is nonsense. It does not exist. Okay, so if you are integrating angular velocity, I mean you can integrate that you can take it to a computer, integrate it, but it is sheer nonsense, because you are expecting the integral of angular velocity to be the rotations, but you have forgotten that the representation of rotation, the derivative of that representation is not angular velocity. Angular velocity is something else, which we will not talk about. A more realistic example, position vector is not a vector. Relative position vector is a vector, and we could prove that in a while, but we won't do it because we are running short of time. Yeah, vectors are useful. Tensors are absolutely useless, okay, because it has been taught in IIT Madras or in any such institute. I can talk ill about IIT Madras on camera, no issues, right? I am sure. No, but I'll bring out the better part of it. Okay, so tensors are useless because I know what is stress. Stress is force by area. Everyone knows that. What are these people, getting into with tensors? So I am very happy actually. Stress is force by area, and I am a happy kid with this definition. I know that force is a vector. I also know that area is a vector because it has some magnitude for sure, and the orientation of that area is a vector. So fine, it's a vector. But here lies the problem. How can I divide a vector by a vector? That my school teacher did not teach me. Okay, I cannot divide a vector by a vector. Come on, it's not possible. MATLAB has some dot divide command, but hopefully this is not the same thing. Okay, so there is no operation of vector division. So how do I do it? So therefore, my university teacher comes and tells me that look at it this way, that instead of saying stress is force by area, you say stress times area is equals to force per unit area also. So this is this stress is the second order tensor which acts on the unit normal n to give me force by the magnitude of the area, which is the traction vector. So this is the new interpretation that the tensor brings in. Okay. Unfortunately, tensors cannot be drawn, tensors cannot be seen, tensors cannot be eaten for dinner, tensors cannot be, I mean, you do not have a quote unquote feel of tensor, okay, but it is there, it is very naturally there. Okay, with the choice of coordinate system, any tensor can be brought down to a 3 by 3 matrix, just like with the choice of coordinate system, you are bringing a vector to a 3 by 1 column vector. And just like anything else in the society, it must abide by the rules of its society. There are rules of tensor algebra, which is addition, subtraction, multiplication, all of this must be followed, and it happens to have the exact equivalence with the matrix rules, because you have represented a tensor as a matrix. The actual tensor is something which you cannot even touch. You have brought it down to a set of numbers which you have arranged in a box like fashion as a 3 by 3 matrix. Okay? So, this 3 by 3 matrix is just the representation of the tensor. Please understand this aspect very carefully. Just like if you change my name, I am sure in the hostels I am called by a different name, but my attributes remain the same, whether I am called Abhijit Sarkar or some dirty name which I cannot say on camera. But the attributes of the quantity is what identifies the quantity. It is not in name, it is not in the Aadhaar number, right. So, that is very important. As I said, tensors cannot be drawn, seen, touched or felt, and any such things, no sense organ can be used to give you this feel, but you have to take it in your thoughts. Okay, so I think I am at the conclusion. No, I have one more slide. Yeah. So, this is the only slide where I have lots of equations, and I know people are ticked off, which is why I say brace, 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 because these are I don't know, it's very difficult for people. At least for some students it is difficult. So, here are a set of equations. Both are supposed to be the same equations, the equilibrium equations. One is supposed to be for the Cartesian coordinates, the other is supposed to be from the cylindrical coordinates. But the problem is both of them look ugly for sure, and there doesn't seem to be any resemblance between the two equations. You are telling me it's the same equation, which is the equilibrium equation, just represented in two different coordinates. Then how can it be that I am not seeing any similarity between the two? Maybe my I power needs a check, but doesn't matter. It is so very different, right? So, again my distress call goes out, that does that mean Mother Nature is discriminating? If you choose a Cartesian coordinate system, you will get a slightly simpler equation. If you choose a cylindrical coordinate system, oops, 1 by r and these quantities pop out of nowhere. So, spherical coordinate system, I could possibly not write it even this slide. If you go to even more complicated systems, non-orthogonal systems, it will be even more difficult. So, the question is, does Mother Nature discriminate between the different coordinate systems? And then more importantly, how many equations does one need to mug up? And is there a mnemonic for that? Because every equation seems different. The answer is again lying embedded in the tensor. The laws of nature should be best expressed in tensorial form. Every coordinate system, I mean, if you forget the coordinate system, just like the actual tensor is something that you cannot touch, you cannot feel, the actual laws of nature expressed in that tensorial form, in this case the equilibrium equation is this. But the only problem associated with this interpretation is that for problem solving this is actually useless, because you need to solve a problem for your exams and for publishing papers. So, for that you will have to bring it down to some coordinate system, because other than numbers you do not understand anything, you and me both together actually. Okay, you have to bring it down to numbers. So, for that the choice of coordinate system is very important. So, the choice of coordinate system is actually associated with the problem solving. Nature's law is this, which is in a beautiful aesthetically appealing equation, which is this, but while doing the problem solving you have to do that dirty work of putting it into some coordinate system of your choice, and then what you will see is a few clumsy terms here and there, but you have to deal with it. There is no other way out. And it so happens that actually nature has not discriminated. Nature has only given, this is the law of Mother Nature. It is true for every coordinate system. The choice of coordinate system is associated with the specific problem that you are solving. If you are solving an axisymmetric problem, best use a cylindrical coordinate system. If you are solving a regular problem, maybe a Cartesian system you can get away with. So, the point is there is no universal best choice of coordinate system. So, you should not actually mug any of those equations unless you know for sure that question is coming in the exam. Okay. Other than that, there is no reason to mark any of those equation. Neither should you mark this one, you should know the derivation of this one, okay, that this is the equilibrium equation. So again, this is nicely brought out in this cartoon. So there are many roads which are leading to the same real truth. It is just that you are getting confused by the very fact that there are many roads leading to the same truth. Okay, I think we'll not take much more time. Conclusions, I'll give you some free advice here. It has been a long talk. The first advice is stay away from theoreticians. They can either crank you out or they can infect you with their passion. I don't know which side of the coin you fall in, but either case, discretion is advised. Okay, what I have learned from my experiences is that nature won't give out her trade secrets easily, and you have to have this persistent love, passion, whatever you call it, to understand the laws of nature. And that's what I call it as selfless, not just for one application, for one problem, which actually requires one coordinate system. Every application, every coordinate system, if you want to look at that big picture, then the tensorial form is better than the indicial form or the component form of it. So that's one takeaway. I hope I have given you examples of real